Chapter 7 details light and color, and what we're looking at is what light is, so the definition of light and how it works, and color, which is the result of light interacting with your eyes and with objects and matter in the world. So the first thing we're going to talk about is what causes color. Now specifically, molecules interact with light. Electrons within those molecules can move farther away from the original nucleus, and as they do so, that is an absorption of energy. And that absorption of energy results in some of the light, which is effectively energy, being absorbed by the object. If you see a color that appears white, for instance, what you're looking at is an object that its interaction with the light is such that it reflects all of the light, and none of the molecules are actually absorbing any of the light. So if the object looks white, it's because all of the white light, which is a combination of all of the different visible colors of light, is hitting the object and bouncing off and reaching your eye. Now an object that is black is absorbing all of the colors of light. So when white light is incident upon that surface, the molecules within that object absorb all of the energy that is coming into them, and none of the light is reflected back, so our eyes don't pick up any light of any of the visible colors, and therefore what we're seeing is the absence of light coming from that particular object. If the object has a color, so for instance, this object is kind of a bluish turquoise kind of color. It's a combination of blue, green, and yellow. So when red, orange, yellow, green, blue, indigo, violet, all of those light colors strike an object as a sample of white light composed of all those different colors, some of those colors are absorbed. So what's actually going on is red and orange and that looks like pretty much it are being absorbed, and the light that comes back off of it is the color that we see as the color of that object. But in reality, the color that's being absorbed by the molecules is the color we don't see, the color that's missing from the white light spectrum that comes back towards our eyes. Now, for the properties of light, there's a couple of things we want to know. One, is that it has no mass. Okay? Secondly, really, really quick, about 300 million meters per second, kind of quick. Don't need to memorize those numbers, just know that it's really fast and that nothing else is faster. That's sufficient. It, kind of like electrons, has both wave and particle type properties, meaning that it has an oscillation that occurs in space of both an electronic, so a positive and negative charge sort of vibration and oscillation, and a magnetic oscillation. So in 3 dimensions, we like to draw these waves as this nice 2-dimensional wiggly line, but light in reality is more of a 3-dimensional kind of an expansion and contraction of a puddle on water, you can kind of think of, and that oscillation is traveling through space at a certain speed with a certain amount of wiggle. And that wiggle is actually an increasing and decreasing positive and negative electrostatic attraction, and a increasing north and south pole magnetic attraction. So because of this, sometimes light is referred to as EMF, an electromagnetic force. So when we see these waves traveling through space, we can identify them with a number of properties. Well, first of all, each little wave that's traveling through space is a packet of energy, and that packet of energy represented by that light, that unit of light, is referred to as a photon. Now, that's the particle-like property. The wave-like property is this isolation in these electronic and magnetic fields. The particle-like property is that it's composed of discrete units of energy called photons. So now these particular units, one way we can kind of quantify the amount of energy present is by the length between one biggest amplitude wiggle of that wave and the next. So that distance from one to the other is just referred to as the wavelength, and is given the Greek symbol lambda. Okay, so that's the wavelength. And what we see is that the amount of wiggle present here is proportional to the energy, and is proportional to this idea of how wide we have to go before we get from one maximum in energy to the next maximum energy in one of these two types of fields. So specifically, the longer we have to go, the kind of lazier the wiggle is, the lower the energy is. We'll look at that as an equation form in a second. But just keep that in mind, that energy is less. That means that the amount of wiggle, or the space between wiggles, is greater, and vice versa. If we have a higher energy wave, what we're going to see is that the wavelength will be shorter because it's wiggling faster. Okay? So here's our mathematical way to say this, is that the two things are inversely proportional. And what we see as color is actually a way that our eyes are able to perceive the amount of energy that the photons striking our eyes hold. And so color is proportional to energy. Okay, so what level of energy is coming at us is seen as that color. And that color is can be described as the wavelength. And for visible light, that wavelength is going to be in the hundreds of nanometers long. So it's a really, really small amount of space between wiggles. But that's what corresponds to visible light. Okay? So that energy is inversely proportional to the wavelength. So more energy, smaller wavelength, less energy, greater wavelength. That's all this whole little relationship means. It's inversely proportional. And so, by the way, the color is what's proportional to energy. The intensity of light, how bright it is, has to do with the number of photons of that particular amount of energy. So it's kind of like if somebody gives you 50 cents. That's not a lot of money. But if they give you 50 cents over and over and over and over and over and over again, that's going to be a large amount of 50 cents, right? A large amount of small amounts of energy. You know, if somebody gives you 50 bucks, that's going to give you more buying power. That has a higher amount of energy in our analogy. But if somebody only gives you one or two versions of that, even though it's higher energy, the intensity of that income of money will be less. I don't know if that helped clear things up or made it more confusing, but just want you to understand that there's a difference between the energy of light, which is proportional to its color, and the intensity of light, which is proportional to how many photons of that particular color reach your eye. Okay, and intensity is what we see as brightness. The frequency is another measurement. We have the wavelength of light, which is the distance between one maxima and another, but you got to keep in mind that this whole wave is moving in some direction. Okay? The photon is moving in a direction. So if we put up kind of an artificial little measuring finish line here, and we watch this wave streak past, it's going to hit a maxima a certain number of times per second as it goes past this imaginary finish line. So how many times we hit a peak in 1 second, so number of peaks that go past some point in space, and that's per second, we refer to as the frequency of the light, specifically measured in hertz. Hertz, Hz, all that is 1 over seconds. So if we can put it all in one line without having to write it as a fraction, it's the times per second, hertz frequency. Okay? We use the symbol mu, which is kind of like a V with a slightly more scripty, wavy arms sort of a thing. And because the speed of the light and the length between waves is going to be a factor in how many waves go past that point in a given moment of time, we actually have a proportionality here, that the frequency of the light is equal to the speed of the light divided by the length between wave peaks. So at conferences where people talk about light chemistry and photochemistry, which is the study of photons interacting with chemicals, there's a joke that people like to use. Since this is the symbol nu, people come by and they say, "Oh, hey, what's new?" And then they respond, C over lambda. Ha 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 ha. Right. So one way to remember it, what's new? Frequency. C over lambda. Now, I am not going to ask you to do calculations with this. What I am going to ask you to do is say things like, if the wavelength of the light increases, what happens to the frequency? Well, they're inversely proportional. So as one goes up, as wavelength goes up, frequency goes down, and vice versa. Okay, so that's the sort of thing that I want you to understand. Just the relationship between the two things, wavelength and frequency. So in terms of visible light actually goes a little bit lower than this, but 400 is a good, nice, even number to stop at. 400 is the blue end of light. Okay, so let me ask you this. A little concept check here. 400 nanometers versus 780 nanometers. These are wavelengths of light. Here we have red at 780 nanometers. That's what we'd see as red light. Which one of these two has the higher energy? A photon of red or a photon of blue? Okay, well, remember, energy is inversely proportional to wavelength. So that means shorter wavelength, higher energy. So it's blue light. Higher energy. Okay? So red light has lower energy. The spectrum has an acronym, the visible spectrum, that helps you to remember the order of energy from lowest to highest. Red, orange, yellow, green, blue, indigo, violet. Alright, I want to point out here that I really can't tell the difference between blue, indigo, and violet. It's not really color blindness. I don't know if I just failed that section of kindergarten or what the deal is, but I can't really differentiate between these, and I really don't think there's a whole lot of difference, honestly, between indigo and violet, but it makes this easier to say as an acronym, so we keep it. So Roy G. Biv gives you the order of lowest to highest energy for visible light. Red, orange, yellow, green, blue, indigo, violet. Okay, so that's the visible spectrum of light. In terms of energy, if you have less energy than red, you can't see it, right? But that's infrared. Less energy. And you've heard of infrared before, most likely. This is IR. Right? We use IR light. This is kind of heat. We can feel IR light as heat energy, so it heats up our skin if it's being incident on your skin, but that's about it in terms of perceiving it. On the higher than blue energy, we have ultraviolet or UV rays. And these are the ones that cause sunburn and skin cancer and that sort of thing. And we have other things that are even higher energy, like X-rays and gamma rays. We have things that are even lower energy than infrared, such as microwaves and the radiation that we use for radio transmittance. But what I really want you to know, the visible spectrum in the order of lowest to highest energy, plus I want you to know infrared is a little bit less energy than visible, and ultraviolet is a little bit more energy than visible. Okay. So how does this all work? Well, when we look at things and we see things absorb, one chemical phenomenon that you can see, photosynthesis is another, but that's a lot more complicated, but you see photodecomposition. If something absorbs enough energy, it will actually start to break down. And the color of something can break down pretty quickly. And that's one way that we actually see decomposition of chemical bonds is through loss of color, kind of referred to as photobleaching. So just for this, if we want to think of an example of this, we can think of those colorful pinwheels that we always have, all those different little things around, and a little circle in the center and a stick. And the wind blows on this and it spins. And each of the little parts of the kaleidoscope wind, I just said the word and I can't think of what it's called now, pinwheel. These little pinwheels is a different color. When you put these in the ground and leave them out there and let them sit there and run nicely for a week or so, what you're going to see is the red is going to fade out faster than the other colors. Well, why do you think that might be? And these are the sort of questions I want you to be able to kind of think about with just what we talked about. Why would red fade out first when exposed to light? Well, think about this. If the object is red, what color of light is being absorbed? Okay, what's being absorbed is all but red. Okay, so red being the low end of the spectrum, that means everything but red is the high energy light. So if we have high energy light being absorbed, we're much more likely to break down the molecules that are responsible for the color that we're seeing, because they're absorbing all this high energy and can break apart and not be able to absorb light in the same way, and therefore start to reflect light, and the color fades away to white. As another example of this, what colors tend to fade most quickly in clothing? If you have bright colored shirts, those can fade, that sort of thing. But if you have black fabric, that fades out to gray almost the most out of anything, even more so than red colors will. It'll fade out to kind of a washed out looking black color. Well, think about that. What light is being absorbed by an object that appears black? If the object is black, that means all light, all of those energy regions are being absorbed. So that's even higher energy than the thing that appears red. And so you can kind of explain a little bit why some colors fade faster than others. Not entirely. I mean, there's the strength of the bonds in the molecule that goes into this as well. But even with that, we have to think about the amount of energy being absorbed. So in terms of damage, though, and sunburn and issues of absorbing in human tissue, ultraviolet light is the most common. That's what we're exposed to the most. Although the X-rays and gamma rays are higher energy, like we talked about on the last slide, so those are an issue too. But mostly what we're going to talk about is UV light later on, which leads to sunburn and ultimately possible skin cancer.